Welcome to today's HPC Café. It's nice to see so many people here in person. It's exceptional, and I'm really happy about it. So thanks a lot for coming here. There's also a lot of people in the Zoom. So whenever you have a question, put it in the Zoom chat. Just speak up, raise your hand, whatever. So let's keep this interactive. I call today's topic Computer Architecture 101 for Scientists, because we know that sometimes people who use our parallel computers or any parallel computer are sometimes challenged or intrigued by the complexity of the hardware they are using. And sometimes they don't even know what to do, okay? They're just using the scripts and setups they inherited from their coworkers without actually thinking what's going on. And that leads to some problems, some of which I will detail on. So I think that it's good to tell you a little bit about how a computer works, how a supercomputer works, and what the basic bottlenecks are that you're up against when running parallel code on a supercomputer. Without going too much into detail, of course, I could talk about this for a week or so without pause. So, bear with me. I think I can keep it below 45 minutes. All right. So that's my plan. I'm going to tell you something about hardware architecture, parallel programs, how they're mapped to the hardware, a little bit about performance, what it is, how we can assess it and judge it, limitations of parallelism. Okay, so how parallel can a program be, and some best practices that give you some kind of guideline, what to do, how to access the performance of your code and the scalability of your code. So let's start simple. This slide shows the anatomy of a CPU compute cluster, and that's a very simple level. We're going to be going into more detail later. But the purpose of a parallel computer, any computer for that matter, is to execute code, execute instructions. And for you as a scientist doing numerics, it's even more specific. The purpose of a computer is to do arithmetic, usually floating point arithmetic. Okay, and that happens in the so-called execution units of a compute core. Okay, each processor today has a couple of compute cores, maybe 2 if you have a wimpy tablet PC, or maybe 36 if you're on a Fritz compute node. But it's always a couple of cores. Each core can execute a program, maybe 2 if hyperthreading is enabled, but let's not go into these details. And this is the stuff that happens to make your program work, to solve your problem. Okay, this happens in these so-called execution units. And these execution units, they do the multiplications, additions, divisions, whatever, that solve your numerical problem. And they make up for a surprisingly small amount of transistors. If you look at the whole computer as a bunch of transistors, then the execution units are really tiny bits of that. Okay, the rest goes into other stuff. The other stuff comprises, for example, L1 and L2 caches. Caches are small, fast memories, and the CPU tries to keep the data that you use very often within these caches, so that if you reuse it from time to time, then you can access the data more quickly. It turns out, if you dive deeper into this, that data transfer and data access delay is the most important performance limiting factor in computing. Okay, so if you can somehow make your program use less data, or use data more that is closer to the CPU, like in the L1 and L2 cache, then your program gets inevitably faster. Okay, so this is the #1 bottleneck, data transfer. That's why we have these caches. L1 caches typically are a couple of tens of kilobytes, like 32, 48, 64 kilobytes. L2 caches are of the order of half a megabyte, 1 megabyte. And so that's the resources that make up one core, okay, that attach to one core. And each core has that. Each core has registers, execution units, L1 and 2 cache nowadays. Now, on a chip, usually we have a couple of cores, as I said, 2, maybe the minimum. Nowadays, you can buy chips with up to 36 cores from Intel and even more from others. And a bunch of those cores are put on the chip, and they usually share a common L3 cache. Now, how much of the cache is shared, that depends on the particular architecture, but usually the L3 cache is not private to each core. It's shared among a bunch of cores, and that's important, as you will see later. So let's say up to 64-ish cores nowadays on a chip, and that's the thing that you put on a socket. So what we call a socket, that's a thing that you buy in the shop. So the CPU that you pay for. Sometimes the CPU comprises several chips. That manufacturers have gone that route recently to cope with the difficulties of making very large chips with very many transistors. They put multi-chip arrangements on such a socket, but the socket is the thing that you put on the motherboard. Okay, if you open your computer, there are usually 2 sockets. This 2-socket arrangement is like a sweet spot in high-performance computing. Usually in HPC, for a CPU-based cluster, we have 2 sockets per node. And one node runs one instance of an operating system like Linux. Okay, so each socket has all these resources, the cores, the caches, and it has usually nowadays memory attached directly on the socket. There were times like 15 years ago when we had separate interfaces for the memory on the motherboard. That's long gone. Nowadays, the socket, the CPU has these memory interfaces built in. Now there are 2 sockets and 2 memory interfaces, which means there are 2 distinct regions of memory on the board, each attached to one socket. And there could be even some substructure, as you will see later. And to make it not too hard for you to program this, there's a connection between these sockets, between these memory domains, that makes it appear as if you had one big monolithic chunk of memory. Okay, so if there are 64 gigabytes here and 64 gigabytes there, it appears to you as if it were one big chunk of 128 gigabytes of memory. So that's a node. That's what you put into your cluster. If you get a guided tour to one of our clusters, that's what you see if you open the door and you can draw it out the drawer. And then finally, you put together many of these nodes using some network to form a supercomputer. Many of those nodes, high performance network, usually InfiniBand, and some storage, which is usually also attached via the network. Okay, it's a shared resource attached via the network. Nowadays, we hardly have any disk resources on the nodes. And some nodes we do because people do work a lot with files locally. But on highly parallel clusters like Fritz, for example, we don't have local disks. Okay, so that's the high-level view on a compute cluster. Now, in reality, this is all much more complicated. Here's a view on a modern CPU compute node with 2 sockets, one left, one right socket. This is AMD Zen 2 Rome. Each socket, each processor has 64 cores. And there's a lot of substructure, which I will not go into detail here, but you see there are groups of 4 cores. Each has its own level 1, level 2 cache. These 4 cores share a common L3 cache, and there are 2 of these 4-core groups connected together on a chip. So each 8-core group is actually a chip, and then 8 of these comprise the full socket. And we have 4 distinct memory interfaces, which makes it even more complicated. Then there's a second socket, which is connected via some hopefully high-performance interconnect. So you see there's a lot of substructure. We call that topology. And it does matter for the performance of your program where your processes and your threads are running. Okay, if 2 threads that communicate a lot are running far away from each other, and they need to communicate using, I don't know, shared memory or maybe message passing, then this is a slow thing. If 2 threads which communicate a lot are close together, they can use the shared L3 cache to communicate. That's much faster. That's one reason, one of many reasons, why the performance of programs depends a lot on where you run your threads and processes. And that's why we teach people always to pin their threads and processes to the resources. Okay, use some sort of affinity. Do not leave it to the operating system or to some default setting to take control. Okay, so that's one node, and it's only a CPU node. Of course, nowadays we have GPUs as well. So we take this node and we use the PCI Express lanes that are available on these CPUs to connect accelerators. In this case, that's a simplified view. Okay, in this case, we have 8 GPUs, accelerators connected to those 2 CPUs. And yeah, I think that's it. Okay, so each accelerator, again, is in itself a normal stock program computer. It has cores, it has execution resources, it has caches, it has memory interfaces. There's a little bit of a different focus there on an accelerator like a GPU. There's more resources dedicated to execution, actually doing the work, and less resources dedicated to something like caches. There's usually a huge memory bandwidth, so that if you compare a single accelerator with a full node, you get a speed up of, well, depending on the exact models, between, let's say, 2 to 8, something like that. Okay, if memory bandwidth or peak performance is the limiting factor. Okay, so that's what a node looks like nowadays. 8 GPUs, 2 sockets. And then we have one node, okay, like an Alex, and we connect these nodes using a high-performance interconnect like InfiniBand. So each of these nodes has a connection to this communication network, maybe 2, There are clusters which have so-called dual rail setups, where two network interface cards are available on each node, and you have two paths into the network. Because the more performance you put into a node, of course, the more performance you need also to communicate with your neighbors. Okay? Because the faster you compute, the faster you need to communicate. So it's a good idea if you pack a lot of resources into a node, also to have more resources to communicate with other nodes. Alex doesn't have that, since Alex is a cluster which is mainly targeted at single GPU or maybe single node jobs. We don't have that there. Okay, and then finally, we need some storage to put the data somewhere at the end of the computation, because all the storage we have in the nodes is non-permanent. Mostly, of course, we could have on-node storage. That's this tiny disk I put here. So that's the local SSD, for example, on the Alex nodes and on the tiny GPU nodes. But the major part of the storage is actually in some network storage, which has its own separate infrastructure. Okay, so there might be a couple of nodes like these connected to some hidden infrastructure that you don't see, you don't need to know about. The most important thing is that this is network storage. So it's one resource that is available to all users using the cluster at any one time, which means this is a resource that if you use it to 100%, nobody else can use it. Okay, that's the only resource mostly that has this property. If you have a node and you do some stuff on the node, nobody cares because it's your node. Okay, if you bring the file system to its knees by opening 10,000 files 10,000 times every minute, then everybody suffers. So that's the basic difference here. All right. So now we have the setup, this complicated setup with all this parallelism on the nodes and in the cluster. And now there are two crucial questions. Okay. First question is, what are the hardware components in this very complicated, this intricate setup that limit the performance of my code? That's important to know. Because if you know what is the hardware factor that limits your performance, you could choose a better cluster next time. You could apply for resources at a computing center that has more of that resource, whatever it is. And second question, what software properties limit the performance of my code? Because it's not only the hardware sometimes, it's also the software that cannot scale better, that cannot perform better because there is something in the software that should be improved. Okay. And then two other questions, how should I know? How do I find out? And that's a complicated question. Okay, I will answer some of it today. And what can I do about it? It's also complicated, even more. So I will only say a little bit about it. All right. So let's start. What we do here is parallel computing. And you saw in this architecture overview that the performance of a computer is generated by parallelism. If you cannot use the parallelism in the computer, you cannot use the power of the computer to solve problems. Okay? So the task of using a parallel computer is to map a numerical problem, a numerical algorithm, to the hardware of this computer. So here's a simple example. This is just a matrix vector multiplication. And you want to execute it on a parallel computer. And this could be your laptop or it could be a supercomputer. Doesn't matter. It has to be parallel. Okay, so you have to map the problem. You have to split the problem into pieces and map the pieces onto the parallel hardware. And of course, this has to go as efficient and fast as possible. So we want high performance. That's the goal. Okay, so what is performance? That's the first question you need to answer. Okay, what does it mean if we talk about performance? So if we have performance, we have a number, we have a metric, we can try to improve it. So what is performance? Performance is work over time. Don't let anyone tell you anything else. Okay, it's how much work I can do in a certain amount of time, period. The problem comes with the definition of these terms. Now, time is simple. Definition of time is simple. It's just wall clock time. It's what you can read off from the wall clock, okay, or from a stopwatch. Don't use anything fishy like user time or system time or accumulated thread time or whatever, CPU time, just wall clock time. That's what's relevant for you because that's what determines how fast your problem can be solved, okay? So that's simple. The more complicated part of this is the work, because there are different concepts for work. One possible concept is how many computations can I do? And computations, we mean multiplication, addition, maybe subtraction, maybe division. Okay, so the simple operations, how many flops can I do per second? Usually the performance of supercomputers is quantified in this metric. How many flops can I do per second? And nowadays, as you know, we have the exaflop era. We have computers nowadays that run more than 1 exaflop per second for a certain workload. But the flop is not the only work metric that's a viable metric. For you, something else may be interesting. You may not care about the flops. You may care about how many lattice types can my code update per second because I'm using some kind of explicit scheme, okay? How many images can I process per second? Because I'm doing a training algorithm that sucks in images and processes them and learns stuff from them. How many nanoseconds can I simulate for the movement of a molecule? Okay, MD simulations. How many iterations does my solver do per second, and so on. Okay? It could also be just one. If you have one problem to solve, then the amount of work is 1. Okay. Simple. So lots of variation here in the numerator, not so much in the denominator. That's performance. Now, performance depends on a lot of things, and we use a parallel computer. So we can split the performance, or we have to split the performance across the components of the computer. And the basic component that executes your code is the core, because a core can execute one thread or one process. So one true statement that we can make is the performance of my program is the performance it has on one core multiplied by the number of cores. Okay, that's truth. Okay, that's absolutely true. But the core is not the only unit I can use for this scaling analysis. I could also say, why not use the socket as a unit? Because one socket is a thing that I can buy in the shop. And the socket has a lot of resources that are, let's say, isolated from the rest of the system. It has its own memory interface. It has its own caches. It doesn't talk to other things if it doesn't need to, okay? So a socket is a good scaling baseline, so to speak. But we could also use GPUs. If I'm using GPUs, then I want to know how many GPUs do I need to get a certain performance level. Or I could use the node, the compute node as itself, because the only shared resource that this compute node has is the network and the disk. Everything else is within the node. So if I use n nodes instead of 1, most of the resources are multiplied. Okay, so it's a natural scaling unit to use the node. Or maybe even some kind of subcluster, a couple of nodes that are connected to a switch over which they can communicate without any blocking characteristic. So how I look at performance may depend on which hardware unit I use as a baseline for performance. And we see this is very important because these hardware units have different bottlenecks that they share or don't share. So we call these hardware units, in terms of performance scalability, scaling baselines. Okay, some people are interested in how their code scales with the number of cores. Some are interested how the code scales with the number of GPUs. So it's different points of view. So these scaling baselines are important. All right, so there's one caveat here. I said this is a true formula, P equals P core times number of cores. However, as we scale the number of cores from 1 to 36 to 72 and so on, of course, the performance per core could change. Okay, if it did change, if the P core always stays constant, it would mean we have a perfectly scalable program. That would be nice. Okay, this is usually not the case. So the P core is actually a function of the number of cores. Now, to assess that and to describe that, we have a metric, and the metric is the speed up. It tells us how much faster can I compute with n times as much resources. Okay, I have a certain amount of resources, and then I multiply these resources by n. How much faster is my program? This is very simple. Speed up is performance with n units, whatever it is, core, socket, GPU, divided by the performance with 1 unit, core, socket, or GPU. All right. Now, of course, in this formula or in this metric, there are simple boundary cases that we can identify that we can easily identify as good or bad or la. So the best case, of course, is if the speed up with n times as much resources is just n. Okay, that's a scalable program. N times more cores, more nodes, more GPUs, n times more performance. 1 over n times the runtime, that's the best case. I said sort of because sometimes there are some effects that can even lead to S of n being greater than n. Okay, but that's not a standard case. That's exceptional. So usually the best case is S of n equals n, perfect scalability. The usual case is, well, S of n is somewhat smaller than n, but how much and how much is tolerable? And I'll come to that later. Of course, there are also worst case scenarios where S of n could be smaller than 1. Okay, this means you put in more and more resources, and your program gets slower and slower. It's not very common, but it happens. And that's really bad because that's a total waste of resources. Okay, if you compute with 100 GPUs where 1 would do and be faster. All right, another metric that's derived from the speedup is the parallel efficiency. It's just the speedup divided by n, the amount of resources, which means for perfect scaling, we have epsilon equals 1, perfect efficiency, which means on average, each unit works 100% of the time towards solving a problem. If epsilon is smaller than n, this fraction epsilon, smaller than 1, this fraction epsilon tells you what fraction of the time your hardware is doing something useful. The rest of the time is spent waiting, okay, not bringing the problem to its solution. All right, so now we have this metric, speedup, and we want speedup to be n. We want linear speedup. Now, the question is, are there any limitations? Okay, could I write any program, could I implement any algorithm so that the speedup is n? And of course, the answer is no. There are lots of possible limitations that make it impossible to have S of n equals n, because programs are not just executing code. Programs are parallel programs, and parallel programs need to do stuff that does not directly relate to solving the problem. So for example, parallel programs need to communicate. If you have several nodes, several cores or sockets, and you have a program running in parallel, then these processes and threads running on those nodes need to communicate. Communication has to happen because data exchange is necessary, for example, boundary exchange, but it's not solving the problem. It's overhead, okay? If I could reduce it to 0, I would do that. And this is denoted here with these red arrows. So here we have a sort of timeline. We have 4 units, again, cores, sockets, GPUs, whatever. And whenever there's something green, okay, that's executing program, executing your code, solving the problem. But whenever there's something red, it means overhead. We do something that does not do flops, that does not solve the algorithm, but well, has to be done anyway. And this could be communication. Each process maybe has to communicate with its neighbors to solve the problem. The second overhead that we are up against here is synchronization. Sometimes, once in a while, most programs need to synchronize. So everybody has to be at the same step, on the same level. And this synchronization takes some time. Okay, even if everybody arrives at this synchronization point at the same time, it still takes time to do it, to synchronize. And the more processes there are, the more hardware you use, the longer it takes to synchronize. This is denoted by these red bars. And then, of course, if you have synchronization, you also might suffer from work imbalance. In this case, we have these green bars, which denote actual work being done. But unit 1 to 3 have a little bit less work. Or let's put it that way, need a little bit less time to do their work for whatever reason. Now, if there's some synchronization point, that means we have a loss because unit 1 to 3 have to wait until unit 4 is finally ready, and then we synchronize. Okay, and these red bits here, they are overhead, they are loss. I could have done some computation if there hadn't been this necessity, this need to do the synchronization. So communication overhead, synchronization overhead, and work imbalance are things that limit the possible parallelism on your code. And it means that S of n is usually smaller than n. And now, of course, if you scale the resources, you might want to observe how the overhead for all these things scales with the resources. And there are some overheads like synchronization overhead that goes up with the amount of resources. So if it becomes more and more expensive to synchronize, and you crank up the number of resources, it becomes more and more expensive to synchronize, takes longer and longer, takes more and more time away from your precious compute time allocation. Okay. So that's an important part of it, and you can set up actually models that describe that on a theoretical level. Okay, so that was quite high level. Okay, we have true work to do and overhead. Now this true work, which I denoted with P here, There's another problem with that, because sometimes, even if your program is perfectly parallel, it doesn't need to communicate, it doesn't need to synchronize, it may not scale, because it may be addressing parts of the hardware that do not scale by design. And here's an example. So here we have two panels. The left one shows the speed up of some code with the number of cores in a node. Okay, in this node we have two sockets. Each socket has 10 cores. That was actually on EMI some time ago. So 10 cores is the socket boundary. And if you only look at the behavior from 1 to 10 cores, we see performance is not scaled. The speed up goes up from 1 to 2. There's decent scaling from 1 to 2, but then it levels off and it saturates. Okay. And that was a program that has no inherent scaling bottlenecks. There's no load imbalance. It does not synchronize. It does not communicate. Okay. The reason for this behavior is that it addresses a bottleneck in the hardware that's not scalable, which is in this case memory bandwidth. The memory bandwidth of one socket cannot keep up with the hunger of the cores for data. And if I use more than a couple of cores, it's just at this limit, cannot scale any further. However, as soon as we go from one socket to two, so from 10 to 20 cores, we get perfect scalability, because going from one socket to the next within a node, we get a second memory interface. The other socket has its own memory interface, remember? And as soon as I can use that, I get twice the bandwidth. That's why this code scales from one socket to two. All right. That's why it's so important to look at scaling baselines. If you want to answer the question, does my code scale? It's usually not easy to answer. You have to give multiple answers. Does it scale on the socket level, where we have this inherent memory bottleneck and also others like the L3 cache, which is shared? Does it scale between sockets? And does it scale across socket boundaries? Okay. And here for this program, we have another plot here that shows scalability across one node. So one node, 2, 3, and 4. And we see even though it scales from one socket to the next, it does not scale across nodes. At some point, also it levels off. But the reason for this non-scalability, when we go beyond one node, may be different from the reason for this non-scalability. The reason for this non-scalability is memory bandwidth. It's a hardware bottleneck that I cannot work around. The reason for the non-scalability of the scaling of the program beyond one node could be several things. There could be a load imbalance. Okay, if I use more and more resources, there could be a load imbalance showing up, or there could be a network problem that's communicating so much that the network communication becomes a bottleneck, and many other things. But the fundamental mechanism is different. So I always have to tell people how does the code scale in terms of scaling baselines. And the basic scaling baseline is a socket, a node, a GPU, a core, a socket, a node, and a GPU. All right. So what are these resources? Can I group resources into a group that scales and a group that doesn't scale? And that's very important to know which resources scale and which don't. So here's a simple picture. This is from a time where we had 4 cores and not 40 per socket, but the principle is the same. In this picture, we have 2 sockets, we have 2 GPUs, we have a PCI Express link, and other I/O resources like the network, disks, and so on. Okay. Now, I'm grouping now these resources into 2 groups, parallel and shared. A parallel resource is something that if my program needs this resource predominantly, then it will scale. A shared resource means if my program is sensitive to this resource, it may not scale. And also, what's even worse, these shared resources are not so cheap to get a higher throughput from. So execution units, okay, and cores, of course. Execution units and cores, that's silicon, that's transistors, and that's cheap. Okay, I can get more transistors every year. So Moore's law is still sort of alive, which means even the performance of my program depends on the multiply and add units in the CPU or on the number of cores, I'm fine. Because these are standalone units. They don't share anything with anything else. If the performance really depends on these in-core stuff, like execution units, then I'm fine. Inner cache levels, okay? If the data from my program can be kept in level 1 and level 2 cache and not any way further out, then I'm communicating with those caches, but these caches are local to each core. So if I use more of that, I get more access performance for this data. Everything is fine. That's a scalable resource. And it's cheap to get. The next generation of CPUs has more cores, more caches. I'm good. Sockets and memory domains. Okay, if my code can scale across multiple sockets, maybe it's memory bound, but each new socket has a new memory interface. That's fine. Okay. Multiple accelerators. If I have the power supply to support that, I could use 2, 4, 6, 8 GPUs and be fine. If the GPU is the only bottleneck. Okay, if the code scales across GPUs, which means there's no bottleneck between GPU and CPU, and there's no bottleneck on the CPU. Everything that happens depends only on the GPU performance. Then I'm fine. Now, shared resources. Shared resources are resources that if more than one agent, so process or thread needs it, there could be a bottleneck. And usually they're also not so easy to scale. Now, the outer cache levels are typical shared resources. The L3 cache on modern processes is not scalable. So if you have multiple cores needing a lot of data from the outer level cache, at some point it will stop scaling. It will not give you more data, not give you the amount of data that you actually need. Of course, the prevalent bottleneck is the memory bus. Okay, I've shown you an example. If you have a memory bound program and many solvers in linear algebra are memory bound, then, well, you cannot scale across the cores in a memory domain or in a socket because it's just not designed for this kind of workload. The inter-socket link between the sockets, this is usually its performance, its bandwidth is in the ballpark of memory interfaces, but not quite. Okay, maybe 2 times, 4 times slower than a memory interface. So if you need to communicate a lot between the 2 sockets, that may be a bottleneck. And to make that bottleneck less impactful, to make it wider, is expensive because you need wires, okay, or higher frequency. That's a complicated engineering problem. It's not cheap. PCI buses, okay, if you can use accelerators, fine, but you need to get the data there and back. And if that's the bottleneck, then it's not easy to solve because the number of PCI express lanes is limited. Other I/O resources like the network access and the disks, of course, are very important bottlenecks that are not easy to scale. We can give you easily more capacity, but it's a little bit more complicated to give you more performance in the file system, especially if it's about small file access or metadata heavy access. Okay, and that's the basic question you need to answer. How does a program react to all these hardware details? And some programs are inherently scalable, meaning there's nothing in the actual execution that limits scalability, but they suffer from hardware bottlenecks that cannot be easily circumvented. Okay, so wrapping it up, what should I do? What should I do knowing all this, keeping it in my head, but not knowing exactly what the bottleneck in my program is? So how should I start? Now, a good way to start is to assess the scaling properties of your program by proper benchmarking. So if you go to a new cluster, maybe you change your setup, you have a new problem to solve, the problem size changes. It's always a good idea to take your previous setup and benchmark it on a new machine, a new environment. So for example, this could be a result of such a scaling run. We report performance versus number of nodes. Okay, we choose the node here as a basic scaling baseline because, for example, in the Fritz cluster, 1 node is what you get. Okay, you can get less than 1 node. It's always at least 1 node, so 1 node is a good scaling baseline for Fritz. And we see that this code scales pretty well for a small number of nodes, and then it levels off, and at some point it even gets slower. Okay, if you use more and more resources. So, where on this line should I stop? That's an important question. So when it still scales, that's good because I'm using the resources to their full extent. And then at some point it stops scaling, still okay, but I'm still wasting some of the resources. And then at some point, especially if it gets slower, I don't want to go there. And this threshold, this point where I can say, I don't want to go there anymore, that's of course a moving target. Okay? And there are opinions on that. So my opinion is anything that's below 50% efficiency is not useful. All right. So if the parallel efficiency goes below 50%, you don't want to go there. There are some exceptions. For example, if you need the memory, if you can only solve your problem with 21 nodes in this example, because 21 nodes give you the amount of memory that you need, then you may accept a certain amount of bad scalability. Okay, but that's one of the few exceptions. Usually I would say 50% or even higher. That's the threshold that I wouldn't cross. We have a particularly striking example of this. Anna Carla has put together some benchmarking data for GROMEX in an HPC cafe some time ago, and there's a YouTube video that you can watch. There's also her slides linked under this link. All right. Now, of course, you can do that whenever you want to do a campaign, a computation campaign of a lot of runs, because you want to see the sweet spot. All right. Another thing that you can see very nicely here is that the less parallelism you put in, the higher the efficiency. If you can put up with a runtime of several weeks, if that's fine with you, then use a single node. Why not? It's the most efficient way to use the hardware. Okay, so probably put it in a blatant way, use only as much resources as necessary to get the runtime to a tolerable limit. If you can wait a couple of weeks for a single run, of course with checkpointing, then do that, because it's a more effective way to use the resources than using 100 nodes with only 50% efficiency. It's a much more effective way of using your resources. Sounds counterintuitive because we're doing parallel computing here, okay, but that's how it is. Another thing, if you change the input, so if you change the geometry, the problem, the nature of the problem, the data set size specifically, then the scaling will change. If you change the data set size, do something smaller, for example, chances are the scaling will be worse, because if the problem is smaller and you distribute it to the same number of resources, nodes, then it has to communicate more often in relation to the computation. So a smaller problem will usually scale worse. Do the same scaling run again for the other problem size, because the result may be different. The sweet spot may be different. All right, so we've talked about scaling a lot, and when it makes sense to stop scaling, okay, I told you it's basically one node. But scaling is not everything. Scaling is important because you want the resources to be scalable and you want your solution very fast. However, scaling does not tell you anything about actual performance. Your program could be perfectly scalable, but still very, very slow. And there are many examples for that. In fact, a general rule is the slower your program computes, the better it will scale. That's a general rule of thumb in high performance computing. Because if you slow down the computation, the communication and synchronization overhead will be less important. So the program scales better. Slow programs scale better. And if anybody tells you my program scales from 1 core to 1,000,000 cores, you should be very suspicious, because typically these are very slow programs. So it may still be that you make bad use of the standard resources of a computer, and the two standard resources on a CPU chip are computational performance, how fast can I compute, flops, and memory bandwidth, because that's what you pay for. You pay for the cores, for the parallelism in the chip, and you pay for the memory bandwidth. That's the basic resources. Everything else is just epsilon. So how can I look at that? How can I assess the performance of my code instead of the scalability? And of course, there are many ways. You can visit one of our courses to learn more about that. For you as a user of the cluster, we have a monitoring system, Cluster Cockpit. Everybody can access under this URL. There was a HPC Café in January this year, where we detailed a bit on how to use Cluster Cockpit and how to look at this data, okay, how to interpret the data. If you have an HPC portal-based account, so if you have an account that doesn't have a password, you cannot go directly to monitoring. You have to use the HPC portal, okay? But you have a link there to the monitoring. It is accessible. It's just a different path. Here's one example that I pulled a couple of hours ago only. So here's a job that it's anonymized. What this shows, I won't go into much detail. The most important things are these timeline graphs down here. For example, this graph shows you the CPU load and the CPU user load, so how much user and system time you have. And from a high level point of view, okay, the load on one node, these are 8 nodes in this job, the load on each node was 72. So this person used 72 cores running 72 threads or processes, and the load was thus 72. So they used all the cores. Okay, that's okay. That's fine. What's not so fine is the amount of work that each node does per second. So here in this graph, we see flops dp, double precision floating point operations per second. And we see that these 8 nodes do a lot of do different work per time. Okay, a couple of nodes do just 100 gigaflops, another couple do 300 gigaflops, and there's one here that does like 250 gigaflops. So there seems to be some load imbalance here. Overall, the job is not too bad, okay? Compared to all the other jobs running on our cluster. I just picked one at random. But this is not too bad. We see this in the two-plan diagram. Here we see whenever a dot, this is a snapshot of the job, whenever these dots are close to one of these roofs, then it's sort of okay. Okay, it means that they use a lot of memory bandwidth and or performance of the cores. Also, the memory bandwidth is very different. It corresponds to this flops graph here. Okay, so somehow these nodes are doing different amounts of work. Maybe we could improve the performance of this code by balancing the load between the nodes. Whether that's possible or not, it's a totally different matter, and we'd have to talk to the user about that. But as I said, this is not too bad as jobs go. There are other users that have much worse jobs. All right. Finally, some other things to consider. The cluster is a shared resource. Okay, so be considerate. Anything that you burn cannot be burned by others. Check your jobs regularly. So there's a large tendency to reuse stuff, and this is computer science, I get it. Okay, you reuse stuff that other people have solved already, but you have to check your jobs. And it's very easy to burn a lot of CPU cycles doing useless work. So check the results of your jobs. If 100 of your jobs ran only for 5 seconds, there's something fishy. Okay, deal with it. Does the job actually use the allocated nodes in the intended way? So a very common problem we see is that people allocate n nodes and only use 1, or even only 1 core. Okay, that's a waste of resources. You may not notice because it still gets you the result that you wanted, but it uses much more resources that you or somebody else could use. One frequent problem with jobs that terminate early is disk quota. So if you just if you're at your disk quota and you cannot write anymore, then of course the job will usually fail. File storage is shared by all users, as I said in the beginning. So that's the one resource that if you use it, nobody else can use it at any particular point in time. So it's possible to use the file system in a way that makes other people suffer. That's very important. We had a HPC Café in January of 22, I think, about this very topic. And I urge you to watch the video and use slides. Okay, so just a little calculation. The minimum total cost for one compute node, counting everything, so the price for the hardware, the cooling, the infrastructure, the people, is somewhere in the order of 50 cents, 50 euro cents. Okay, that doesn't sound like much, but if you use one node for 1 year, that's 4,000 euros. And if you use 300 nodes for 1 day, that's also on the order of 4,000 euros. So there's a lot of money here. It's not just about the money, it's about the resources. This is money, this is resources that nobody can use if you misuse them, and you cannot use them. So if by a simple change of your setup, just by reducing the number of nodes per job by a factor of 2, you can make better use of your allocation. It means more science for your allocation. So that's a very simple measure. And I could say maybe that's the most important take-home message from here. Do those scaling runs. Okay, find out where the scaling stops and stop there. And use as little resources as possible per job, because that's the most efficient way to use the clusters.
Hi. So I work as a part of the big physics collaborations where we do a lot of computing power on different clusters, and people have tried to also evaluate what the impact in case of like in terms of sustainability, like the power you use it and stuff like that is. Like you excuse me, you mentioned that there's a monetary cost to this, right? But that's also power that's being used, and so there's some agencies that provide funding in some countries that have at least asked to provide reports on that. I don't think this is the case in Germany, but I wanted to ask if that's something that's monitored too, or if that,
Yes.
because that's also like it relates to performance, right? As you mentioned, but yeah.
I think it's maybe not, yeah, it's here, CPU power. So we do monitor CPU power.
Yeah,
We don't provide you like a joule per job reading yet at the end, but we could do that. This has been discussed. And in the future, you may be getting not CPU time or GPU time, but you may be getting allocations in terms of joules.
Because it matters like where you run your job, if it's the right cluster and architecture for it. And like, we have a lot of jobs that work on GPUs and on CPUs, and of course, in total wall clock time is faster to run them on GPUs, but it might be cheaper in terms of power you use that should run them on a CPU for waiting. So that's an interesting method.
It's a complicated, multi-dimensional problem, because how much performance hit do you want to suffer for a power gain or for an energy gain? That's something that you can only answer as an individual scientist. How much do you want to suffer? And secondly, as you say, if I use more resources on the node, I get there quicker, but I also burn more joules. And where's the sweet spot? And also the question, how should I set the clock frequency? Some codes do not even suffer if you set the clock frequency to the lowest possible value on Fritz, 1.2 gigahertz. Some codes don't even feel that because they're memory bound. And you can save a lot of energy by reducing the clock frequency. Okay. Right now, we don't make you suffer for using a lot of energy. That may change in the future. I don't know.
Yeah, that would have been my question. Like when you observe that some jobs are really not efficient, will you step in at some point?
Yes.
Or,
So usually with the low-hanging fruits, not like this. This is not too bad. Okay. But if we see, for example, that there's a blatant mistake, using only one node where they allocated 10, or not making use of the GPU, although it's a GPU job, then they get a ticket. Usually it's just an oversight. Most of these cases can be solved in minutes.